Welcome friends to my YouTube channel. Now on my last lecture I have told about the Galilean invariance and there I told that length is invariant, acceleration is invariant and the laws of conservation of linear momentum is also invariant. But velocity is variant, okay, that I told. So actually, now in today's lecture, I shall going to start the rotational motion, that is the rotating frame of references. Previously, I told about the translational motion of frames. Now, in today's lecture, I shall going to discuss the rotation of frames. Okay, so let's start. Now, suppose you take an inertial frame. Okay, suppose there is a inertial frame. Okay, say this is x, say this is y, and this is z, and this is the coordinate center O. Now we choose another frame s dash. Okay, okay, say this is y dash, x dash, z dash, and this is o dash. Okay, so this is say s frame, that is inertial frame, and this frame is s dash. Okay, so s frame is inertial frame. Okay, suppose there is a particle in s dash frame. Okay, suppose there is a particle in s dash frame, so just join these centers. Okay, okay, this. Okay, fine. Now if the frame s dash is moving with a velocity, say v, moving with a velocity say v0 with respect to s frame. Okay, suppose s dash moves with a velocity v naught relative to s frame. Okay, okay, the s dash is moving with a velocity v naught relative to s frame. So suppose o dash p, this is r dash, op this equals to r. Okay, and o dash this is simply r naught. Then what we can write from the figure, this plus this equals to this, that means r this equals to r naught plus r dash. Now again I tell that what is r? Position vector of p relative to s frame. What is r dash? Position vector of p relative to s dash frame. What is r naught? The frame s dash. Okay, the position vector of s dash related to s. Okay, so if you differentiate this, that is v, this equals to v naught plus v dash, or more commonly if you want to find the acceleration, that is a equal to a naught plus a dash. Okay, so what is a? Acceleration of the particle related to s frame. What is a dash? Acceleration of the particle related to s dash frame. And what is a naught? Acceleration of the s dash frame related to s. That means s dash frame is rotating. Okay, so this we must have to know. Okay, so this is the first thing that we should have to know before starting the translational motion of rotational motion of frames. Okay, now as I told earlier that the Newton's laws of motion are hold good in inertial frame of references. So what will be the force acting on the particle relative to s frame? That is ma. Okay, so we can put a naught plus a dash. So this is simply m a naught plus m a dash. So this is simply ma naught plus f dash. So what is f dash? Simply f minus ma naught. Okay. So f dash is what? Force acting on the particle relative to h dash frame. Now a close look on this equation. F dash can also be considered as an inertial frame provided if we add some fictitious type of forces with F. Okay, we can also treat this frame, that is H dash frame, as inertial provided we have to add some fictitious type of force with F. Okay, so H dash, so if we add fictitious forces with F, then F dash, or more commonly H dash, can be treated as inertial frame. Okay, fine. So if we add some fictitious type of forces with F, so in that particular case F dash is also the force as experienced by an observer in H dash frame. That means in particular case H dash can also be treated as inertial frame. So these fictitious type of forces are known as the pseudo forces. Okay, these are known as the pseudo forces. Okay, so these are known as the pseudo type of forces. Now you all know the example of such pseudo type of forces, that is the centrifugal force. Okay, this is a pseudo type of force. Okay, so the first example, you take the centrifugal force. Okay, what is the expression? That is minus m omega square r. Okay, and you also heard this force, Coriolis force, that we understood later, Coriolis force. Okay, the expression of Coriolis force is this. Okay, this. So these are all fictitious type of forces, and actually this type of forces comes due to the acceleration of rotating frames. Okay, so acceleration of frames is responsible for generating pseudo forces. Okay, so acceleration of the frame is responsible for the generation of pseudo forces, and the familiar example is this. Okay, so this is the centrifugal force and Coriolis force. Okay, these are the examples. So now let us come to another issue. Suppose the earth is rotating about the ns poles. The earth is rotating about the ns poles with an angular velocity omega from south to north. Okay, and a frame h dash is rotating with angular velocity. Suppose we know this, that earth is rotating about the ns poles. Now we consider a frame h dash is rotating with respect to an inertial frame. Okay, so h dash is rotating with respect to an inertial frame with, say, angular velocity omega. Okay, suppose an h dash frame is rotating with respect to an inertial frame with angular velocity omega. Now Now this is the radius of the rotation. Okay, so if we join this, okay, say this is a particle A, so this is the radius of the orbit, say AOB. Okay, so we can express any vector r in the s dash frame in this way: ix plus jy plus ky. Okay, since the frame s dash is rotating with angular velocity omega, okay, any vector r in that particular frame, that means in s dash frame, can be written as in this way. Reminder one thing, that ijk also rotates, since we consider the rotation of frame, okay, in this way. Now suppose, okay, this is the position vector of the particle A relative to O. Okay, this is the position vector, then the velocity will act in this direction tangentially, there is dr dt. Fine. If r is the position vector of the particle A relative to O, then this is the velocity dr dt. Okay, now if this is theta, this is r sine theta, so we can simply write as dr dt, this equals to what? Omega r. That means, oh sorry, if I cap is the unit vector, because there we have to consider the rotation of the unit vector, sorry. So if I cap is the unit position vector of the particle A relative to O, then what would be the velocity at that point? That is simply di cap. Here we consider the rotation of unit vectors. Okay, so di cap dt will be the velocity at this point. Okay, fine. Now this is the velocity and this is omega r. That means this is omega I sin theta. If this is I cos theta, this is I sin theta. And what will be omega r? Omega multiplied by I sin theta. So that means omega cross I. Okay. So similarly, if you take the y component, you can write as omega cross j. And if you take the k component, you will write omega cross k, the rotation of unit vectors. Okay, so why I am writing this, it will be clear to all of you. Okay, here we consider the rotation of the unit vectors. Now, as I told earlier that the unit vectors are also the variables, so we can differentiate this. Okay, so what will be my v? That is simply I cap dx dt plus j cap dy dt plus k cap dj dt, plus you can write x di cap dt plus j dy dj cap dt plus z dk cap dt. So this term you can consider as, say, del r del t. Obviously position coordinates are involved here, so take this term as del r del t. And if we substitute this is omega cross I y, this is simply omega cross j plus z, this is simply omega cross k. Okay, so this is simply del r del t plus, this can be written as omega cross r. So clearly the velocity of the particle relative to s frame, that is dr dt, that can be written in this way. Okay, that can be written in this way. Okay, that can be written in this way. So this is the velocity of the particle as observed from s frame. So what will be the acceleration? Okay, what should be the acceleration of the particle relative to s frame? Similarly, if you consider this, so that you can write as dv dt. So this simply you can write as del v del t plus omega cross v. Okay, with similarity from the previous equation. Okay, so del t, what is v? V means dr dt, that means del r del t plus omega cross r. Okay, plus this is simply, this is del r del t plus omega cross r. So this is simply del 2r del t2 ddt of a cross b, a cross db dt plus da dt cross b plus omega cross del r del t, that means 2 term, plus omega cross r. Okay, now suppose the frame h dash is rotating with constant angular velocity. So under this condition, this term is 0, because omega is constant, this term is 0. Now what is this? This is a dash and this is rest terms are a naught. Okay, now what is del 2r del t2? This you can write a minus 2 omega cross del r del t minus omega cross r. So what is this? Acceleration of the particle relative to s dash frame. This is acceleration of the particle relative to s frame, and these are the other terms. So if you multiply it, so this is the force experienced by the particle relative to s dash frame. Okay, so if you multiply with m, so that you have to multiply the entire term with m. So ma means f, okay, minus these are f naught. Okay, okay, so this is the expression. So what we get, comparing with the previous expressions, that is a equals to a naught plus a dash, we get this, that we get the or you can say as force, this is q, we get this minus 2 m omega cross del r del t minus m into omega cross r. So these are the pseudo forces terms. Okay, this term is known as Coriolis force, and this is known as the centrifugal force. So this is how the idea of these forces come. Okay, that I told. Okay, so in this way these pseudo forces comes into play. Okay, due to the rotation of frames. Okay, and here we have to consider that the unit vectors are also rotating. Okay, relative to an s frame. Okay, so in our next class I shall going to discuss about few other issues related to these pseudo forces. So like, share and subscribe my channel to get latest videos. Okay, and if you have any query, then just write it in comment section. Okay, so thank you.